All right. So the formulas in here only work if ZL and ZO are both real, and SWR and the reflection coefficient are both real with no complex parts. But what if there are complex parts? So that's what we have to tackle here. Now, first part is that only the reflection coefficient can be complex. The standing wave ratio can only be a real number. So in here, the reflection coefficient needs to be absolute valued so that we can only grab the magnitude of the reflection coefficient in here. In here, the absolute value is rather inaccurate because absolute value means differently in complex. So we would have we would have an additional ZO minus ZL over ZO plus ZL. That's the formula there. What does it mean for a complex reflection coefficient? Well, a reflection coefficient is essentially, this is the load, essentially the phase of the load as it exits out of uh, the load, right? Because the load, because the reflection, the reflected voltage travels back to the source. So the reflection coefficient not only encodes how much the how much the magnitude of the reflected voltage refers to the incident voltage, but also how much the phase changes. So if we find the polar form of the reflection coefficient, we would get the magnitude of the reflection coefficient angle, and then the argument or phi. There we go. The phi of the load, right? So that's the angle when it leaves the load. Now, what if you need to find the angle as it goes here, right? So the wavelength travels the reflected wave travels here at the speed of light in that medium. So somehow the speed of light has to come somewhere, right? Actually, the formula for the angle in here, if we know this to be the angle on the load, and then this is our new angle that we want, this is actually the angle minus 2 times beta s. Beta from earlier is the phase shift angle. The phase shift angle is 2 pi radians over the wavelength, which matches the description earlier that this is the change in phase per meter, and the unit of the wavelength is in meters, right? In degrees, this is 360 degrees over lambda, or the wavelength. Alright, let's erase that one. If this is the phase shift constant, this is the physical distance. The physical distance that the light has traveled onto that part. So the length in here is s. That is the physical distance. Beta s is the angular distance. So beta s is angular distance. How much phase the wave has traveled along this path. And this is perfect because we want to find out how much the phase changes up to here. So that is the formula. Now, if you want to find the s, knowing that the phase has changed here, we only need to isolate s here. And actually, the answer would be the phase in the load, the reflection coefficient. This is the argument of the reflection coefficient, the angle, minus the phase on where you want it over 2 beta. Now, remember, every 180 degrees or every half wavelength, this changes. So, we have to add 180 degrees if you want to find the second part right here, where where the phase also repeats. Or you can have 360 degrees for a full wavelength. Alright? So, there we go.